So let's look at this. Here's a typical tensile mechanical stress strain load cell. Here you can see there's a crosshead. This is something that may be programmed to advance at a certain rate by a mechanical motor. And there could be a grip portion that may have some threading, for example, and a specimen could be fabricated to have threads there. And there would be a thinner portion of that material that would be defined very carefully in cross-sectional area and the shape here. And this sort of thinner portion where the force would be focused on the specimen is called the gauge portion. So the length that is all uniform there would be the gauge length, therefore. Opposite, there would be a grip to hold the rest of the test specimen, and then the opposite sort of load cell here, where things like Newton meters to register load would be installed. You yourself can do load testing on your finger. So if you were to pull on your own finger, no jokes here, folks, you can see that your finger can extend a little bit out of its socket a little bit. You might even see a little dimple at the knuckle. And so you are clearly putting extension on your finger. And if you were to let go, it would come back and restore back to its original spot. So that is a linear reversible loading of your finger as you pull on it. Now clearly, if you pull too hard on your finger, you know that eventually your finger will register permanent deformation in that it will come out of the socket and perhaps trigger a visit to the hospital. But that we'll see those same things, those same ideas, permanent deformation in our tensile tests as we consider our stress strain curves on matter. So you might draw your analogies or your thoughts back to that idea of pulling on your finger to think about what some of the features in a stress strain curve might be. Okay, so we've defined stress a moment ago. We saw that that was the force applied divided by the cross-sectional area, A naught. So that is, of course, under no load. So we measure the cross-sectional area. So if this were a rod, there might be a cross-sectional area that is represented by a circle. And that would be our normalizing factor for all the forces applied to our sample. Okay, and we saw that we were going to call this sigma. That was equal to the force, in this case, a tensional force applied divided through by the cross-sectional area. And of course, some deformation is going to occur. So we're going to extend the object from its original length. So that could be represented here from the gauge length portion. So we may have L. And then if it's under no load, we can give it L naught, some original length there. And as we apply increasing amounts of force, we'd expect the gauge length to enlarge due to the applied force. And of course, that's going to give us L under load minus the original length for a delta L. And if we divide that through by L naught, we have epsilon, which is our strain. Notice I'm using here engineering strain and engineering stress. These are additional terms we apply here to show that we are relative to the initial length and cross-sectional area. We'll see at a later lesson that we can replot this information per the actual dimensions of the sample as it's being loaded or strained. But for now, we'll just consider the general stress strain curve as that being an engineering stress strain curve where we are relative to the original dimensions of the sample, cross-sectional area A naught, and original length L naught when there was no force applied, no load applied to the sample. Okay, so most stress strain curves are going to have a general shape that there'll be a linear portion to some limit. This might be you extending your finger to the limits you can to cause a little dimple on your knuckle. And then at some point, the material is going to start to deviate from that linear trend. Okay, so if you imagine at this point releasing your finger, it would return more or less to an area where there is no stress, no force per cross-sectional area, but now you've registered real permanent size change, permanent length, and it has not restored to its original length. So that would be where your finger would have overextended out of its hand, and you've got to now visit the hospital to deal with that. Okay, so moving on, we're also going to see this curve eventually move to a point where the test work may fail. So there's going to be a fracture point here where the sample may break right in half. I'll let you think about the consequences there if you're going to your finger analogy. So that's a key feature for us to look at. Other characteristics on here are the highest data point on the curve, the limits for where deformation is started to register. So we're going to see a careful measurement there. And of course, the portion that is linear versus the portion that is not linear are some other features here that we will look at in this data set. Okay, so moving on, and now perhaps thinking about simply tethering a bar and applying a mass to that bar. And so we'll think about studying the bar as it's undergoing a tensional force due to the mass on that bar. We might have the load, so that might be the load due to the mass of the object. Okay, and then as we might expect, that bar would elongate a little bit due to the mass on that bar. Okay, so our bar here is going to get a little longer due to the mass of that bar. So you might be used to those ideas from previous thoughts or classes, and hopefully now you're getting more used to the idea of going to a stress strain curve where we know that we have stress sigma, that is the force applied, that is force due to the mass of the object, divided through by the original cross-sectional area of the sample, A naught. Okay, and then strain, here are the important features, of course, the original length of the bar, and we're going to register changes in that length via the elongation ideas due to increasing amounts of mass on the object, or on the bar, for example, and that is going to come into our unitless dimension, our x-axis, which is strain, symbol epsilon. Okay, so let's just clean some of this up so we're ready for some of the next ideas. Okay, so with those ideas, let's think about what some consequences of this experiment are. Well, hopefully you recognize that by applying more mass to the bar, tethered to some surface like the ceiling, so if we're increasing the mass, that the stress is directly proportional to that. Okay, so stress is directly proportional to the applied weight in that analogy. Second, how about the cross-sectional area of the rod? So if we were to be able to increase the area of that rod, what would happen to the stress? Well, we see here that making the denominator larger is going to have the opposite effect on stress. So that is, stress is inversely proportional to the cross-sectional area of the rod. Okay, so you as a design engineer perhaps could make a recommendation to increase the cross-sectional area of a rod if you need to apply more mass to it in some later engineering problem. Okay. Hopefully you see here from these ideas that the stress has nothing to do with the length of the bar. Okay, it's only the cross-sectional area of the bar that is coming into account here. So it doesn't matter how long you make the bar or how short you make the bar, it's the cross-section of that bar that is key to the characteristics of the curve, the stress strain curve. Okay, so stress is not related to the length of the bar. Okay, so some other ideas here. What if you were to double the cross-sectional area of that bar? What would you expect to happen to the stress? So hopefully, from the earlier thought, if we double the area, that is increasing the denominator, we're decreasing the stress. Okay, so perhaps we were at a condition here when we had the original cross-sectional area of the bar. And so if we're going to now switch the bar to that one that is much wider, a larger cross-sectional area, we know that the sigma will shift to a much smaller value. So we'll come down to, say, 200 instead on our stress strain curve. That also means that our strain, which was originally, say, about there, has now decreased to a lower value as a consequence of that different bar that we're considering in this experiment. Okay, so you choosing a larger cross-sectional area rod, you are expecting a decrease in the condition now for stress versus what you had with the skinnier rod, and consequently the strain is reduced. Okay, next. How about if you double the mass of that bar? Well, we saw that doubling the mass is going to effectively double the force here due to the gravitational forces on that mass. So double the mass on the bar, you are clearly going to double the stress. So we're going from, say, the square data point here at 200, and then we're going to walk up higher on our graph. So we're now going up to about 400 megapascals on our stress strain curve. And of course, that also means that we're applying more strain to that bar. Okay, and a final thought here. So what about if we were to double the length of the bar? Well, we had the idea earlier that stress is not related to the length of the bar. So hopefully it makes sense to you that there's going to be no change to the stress. Okay, and because the delta L is a function of L naught, we're also expecting no change in the strain of that bar. Okay, so the length of the bar, doubling the length of the bar will have no change to either the stress or the strain.